Was it?
In the IETF, in the page of the IETF.
And?
Yeah, enter. And then we have to look from there. You can put your name. No, doesn't matter. We start now. Okay, we should start. Hi, good afternoon. This is the ROLL meeting. And welcome. Okay, for this meeting, apply the not well. So please read.
You feel like those flight attendants say very important things and nobody's looking on. So, okay, please have a look.
They stand up and move.
Yeah?
They stand up and move.
Oh yeah, okay.
Yeah, exactly.
So, yeah, the slides are already in the internet. Okay, this is our agenda. There is some comments? No? We can proceed. Okay, for our milestones, we have done the routing dispatch work. And we have the use of REPL information in working groups last call, so please comment on the mailing list. And then in January, we are going to recharter or close. No, actually.
For the working group last call, we have had very little return. So I really encourage you to, especially after the nice talk by Michael that's coming, to comment on the draft and at least try to read it and send your comments like I've read it and I approve of this for the publication of this draft. It will be very welcome indeed. Thank you.
Okay, this is the state of the active internet draft that we have. Amy is in editorial queue. The applicability template is going to be like expired. Routing dispatch is in IANA. And use of REPL information is in last call. And we don't have right now open tickets. Okay, they are related internet draft. Most of them they are going to present today.
May I?
Yes, sure.
Okay. Lots of these drafts are not just working group drafts, but they certainly are mentioned in the charter, which is still to be approved. So we will ask you for, if you are really interested in the drafts, if they should become working group. So we will ask after every presentation what you think about if it should go forward, which have to be confirmed on the mailing list afterwards, of course. Yeah.
Thank you. Okay, we send the charter to our area director, and we got some comment back, and we edited the charter. We sent to the mailing list, and These are the modifications. So please read the charter that is in the mailing list and send your comments. Thank you.
And if you don't
Yeah.
hear anything, we will push it forward to IESG. So, thank.
Yeah. Michael is going to present the status of this draft. Thank you.
Hi, so as was mentioned, it's been in working group last call. Prior to just prior to the last IETF, Six-Man made some interesting changes, which were very helpful to us. In particular, allows us to leave RPI headers in on the assumption that they will not be processed, whatever that means. And you can go to Six-Man and enjoy that debate. So that's really all that the most of what's changed in the past 3 or 4 months has been editorial, clarifying of some terms. We had a lovely review from Peter. Thank you very much about some of the things that are still missing. And that's really it. Again, it is a long document and it takes a bit of effort to understand. And there are some really good slides that we had in the last IETF if you need help, because they're animated. And I really suggest you take a look at it, because it really does define something that's been missing in this working group, is exactly what the data plane looks like, and this clarifies it, I think, a great deal. That's really it. Not a lot else to say. We'd like to publish it, get it done.
Comments?
Anyone read it in this room?
Yes, that was the question. Good.
Wow, okay, cool. You got some questions there. Good.
So Rahul Jadhav from Huawei. My question is this decision of leaving the RPI
Yes.
intact while moving it out of the network, the 6-LoWPAN network or whatever.
Yep.
So this decision reduces the complexity, as I understand, after reading the draft. So
Yes.
apart from there, is there any, why was this decision? It is possible for the edge router to remove the RPI header. So why was this decision taken to just simply allow it?
It's not possible for the edge router to remove the RPI header, because headers may not be inserted or removed in transit. Okay, so that's an important thing. And whether or not that rule is changed or not by Six-Man, it has until very recently been believed to be firm. Okay, the difficulty was that, given that we can't remove it at the edge, and given that the header has been marked as critical, or it's a header, an extension, a hop-by-hop extension marked critical, given that it's been marked critical, then the next router that does not understand it, according to historical understanding, would it be expected to drop the traffic. Therefore, any traffic that unintendedly escaped would be contained. Okay?
Okay.
The downside is that, of course, we would like to send traffic. The whole point of a mesh that's connected by IP is that you might like to send traffic outside of that mesh. So, in order to be able to remove it, what we discovered was that we had to put IP headers in, which has a significant cost, and which we then have figured out how to compress such that we can remove them. So now that we realize that we are not obligated to remove that header, then a number of scenarios where we require to put an IP header in become not so critical. Okay.
Okay.
And that's really important, because it turns out there's some other scenarios independent of sending traffic to the quote internet. If you have what are properly called hosts, or sometimes in this working group we call non-RPL aware leaf nodes, right? Those may not necessarily understand that header. And if we would like to send traffic to them, then we need to know when to remove that header. And we were faced with the difficulty that in many modes, in particular in storing mode, we don't know what the node before the end header node is. And since we don't know that node, we wind up having to put hop by hop IP headers, which means we have to remove them at every hop and add them at every hop. Okay, so that's a bit of a pain in the ass. It's complicated to code. It seems dumb. It's redundant. No one implements that, and so in the end, so what our document in the end does is it makes it clear you don't need to remove them, and that the end node will deal with them. Okay.
Right. Pascal Hubert, there's a few things which are still in flux, and there is now the influence of the new 6-layer-H on coding, which might actually change the deal a little bit. First thing is, for 6-man, nothing is really cast in stone. I think the consensus right now is that the update of 2460 will not change anything dramatically, because you have to go to internet standards. You don't change the way things behave. So I think the consensus about going producing new specs about what you can do and what you cannot do, and the arguments against inserting headers don't necessarily apply to removing headers. So what I'm getting at is, if you've got this packet coming from the LLN going outside the LLN through the root, I think it's still, if the root can, the best practice for us should be to remove that header. Now, doing that in the uncompressed form is probably cumbersome. But if you look at the way we designed the compressed form, it's really designed so that you can play this sort of trick. For instance, the routing header, the RH3, when it's compressed with 6-layer-H, it's replaced at the beginning of the compressed form, so that you can really remove addresses as you consume them. Right? And the next thing you find, and if you don't have in the packet going out, you don't have a routing header, the first thing you find, if you have a packet which does not have IP in IP, right? That's what we're getting at. We don't have IP in IP, but we've got an RPI. Well, if you look at the compressed form, the RPI comes first, which really tells you that at the moment where you expand the 6-layer-H into an IPv6 packet to go to the internet, you could actually cut it out.
You could cut it out, yeah.
Right, and just ignore it when going to the internet. And I think at the moment, with what I know, the best practice should be, don't do IP in IP for a packet going out. If you know that's going out, don't do IP in IP, just do RPI. But at the root, snip it out.
So that could happen. I'm not disagreeing with you. And the document, as it says right now, essentially says, don't do, for upwards traffic, don't do IP and IP, just do RPI. That's true for storing and non-storing mode. And that's nice. It's a single transmit path for upwards traffic. And the decision as to remove it or not is a decision at the root, which is probably more capable, more configurable, and more upgradable. So that's in some sense a decision by the operator to do that. As for the arguments for removing the headers, are probably not as strong as for inserting. Certainly one of the arguments is that it breaks path MTU is not true. That it breaks authentication header is true. That this may not be relevant because it's not clear we're using AH headers ever, but there may be other things that matter. So I'm comfortable with it is, and I'm uncomfortable with the fact that we can send them out to the internet and not break the architecture as it is. And I think that's a good scenario. One of the questions I know we did get from one of the reviewers somewhere was how we know whether we're using this this formulation or the other one. And I know that the 6-layer-H got the same question. And essentially, my answer is, well, we know that the 6-layer-H is deployed by fiat. You know, you decide you're doing it, it's on, and that's it. There's no flag days. But essentially, if if a node needs to know whether or not it can follow the use of RPI rules or whether it should follow some historical process, then I would say, well, if it's doing 6 low RH header compression as we've described, then it should follow these rules, and that's the reality. Whatever was happening before is some other scenario.
Right, and just for the Pascal Tuber again, for the point of AH, the same discussion applies to snipping out addresses in the routing header as the packet progresses down the non-storing network. And so that's been a debate as well. And what passed ISG now, because it's in the RFC editor queue with the 6-layer RH, is that we actually snip those addresses so as to save energy, etc., etc. And there's a discussion in the future RFC about the fact that it breaks AH with the fact that we don't have a specification for AH in those networks anyway, so there's no plan to use it. And the only value of using AH with routing header is that it's the rule by 2460 that if you want to reverse the routing header to go the way back, then you need to have proven it by AH. I mean, that's the value of AH. There's no other value.
For that header. There may be some value for some other header.
Yeah. But so far we don't. Yes, that's true. But as soon as you get routing header, we are breaking
I agree with effectively the rules for removing headers are as weak as for inserting headers for our point of view, and I think we could do that. I think that we should write that down as a separate document and have a separate debate over what the 6 LBR should do on outgoing packets. If you feel strongly that it should remove the RPI, then I think we should write that down separately as a separate document, because it's essentially decidable by the 6 LBR independently of any of the other decisions.
Okay, that's what I was getting at, and my point was we should have a recommendation in this document about that. But
you think we should say something there?
Well, somebody has to say something somewhere, right? I mean, I agree with the way the document is worded so far that we don't do IP in IP. I think it's safe. But now what do we do with the RPI? I think it's always safer not to keep it in the IP packet. I mean, what's the point in putting it? I mean, at least, if you've got a 6-layer RH formulation, it's very easy to snip it out. It's actually more complex to keep it because you have to re-encode it into the uncompressed form. If you have a non-6-layer RH packet, I would say, okay, processing the packet is always a risk, so why don't you pass it on? So keeping the capability to either pass it on or not pass it on. But I would say basically the recommendation would be 6-layer RH, you snip it out, plain packet, you keep it, something like that.
Can we continue this offline?
Please, Pascal, could you suggest some paragraph to add to the document about this? Yeah, I mean,
I feel that will drag this document into the 6-man morass, and so that's why I would propose that we do this as a separate document and we wait 3 to 5 months for 2460 BIS to settle, and then we will either point to the resulting thing and say it says we can do it, so we're doing it, or we won't, and that gets us out of. Otherwise, I think that we're going to get blocked on a review somewhere, or.
But I would not like to ship this document saying, do put, at least if we do like 2460, we don't say anything, but saying, do keep the RPI in the packet as you forward it up.
We said you can keep the RPI in the packet as it goes out. You don't have to remove it by putting IP header. We didn't tell you to remove it. We said you can leave it in, right? So there. So Alvaro, do you agree with me that I think we're stepping into a disaster if we go somewhere else, or do you think I'm wrong? It's over.
Alvaro Retana, I don't know exactly where 6-man is, so yes, we may be heading. We may not. So yeah, I don't know. I'm sure that most of you probably follow 6-man a lot closer than I do, so I'll let the working group decide whatever you want to do.
Okay.
Yeah.
What I'm hearing is we should ask Suresh. Okay.
Okay, thank you. We could create a ticket about that, so we can keep working on that as well. just to track this?
I'd like to get be done with. That's what I would prefer. That's why I don't want to open a new issue. But I mean, tell me how strong you feel about it. I think that we could easily write this as a later document because I think that it's upgradable by the root, and the root is relatively easily upgradable versus the firmware. This decision has no effect on the small devices out on the edge of the network.
Okay. Thank you very much,
Thanks.
Michael.
Thank you. And please read the document. I mean, that's important enough to read it and send some comments then, please.
Thank you very much, Michael. Our next topic, LDV Ripple with Charlie Perkins. Microphone.
So I have to tell you when to change slides?
Yes, yeah, we know. Here.
No, that's a microphone.
I need the.
Yeah, you need to sing into it. I don't see it.
No, I need the. Okay, I can.
Okay, well, I'm Charlie Perkins, and I'm here to tell you a little bit about the updates to our document, AODV Ripple. And it's sort of a new take on the P2P or peer-to-peer use of Ripple. And there's an experimental document, RFC 6997, but AODV extends the functionality from that document. So we support story mode, and we have both. Oh, wait a minute.
Charlie?
Yeah. Oh,
Now it's working. Thank you.
okay. Boy, things change fast around here. So we have a support for symmetrical and asymmetrical, but still bidirectional links. And this approach avoids the requirement for having an address vector, as in from the previous document, P2P RPL. So the way it is, we have route request message and route reply. This is more or less adapted for use with Ripple from the work that was done on AODV and AODV version 2 and another working group. And oops, now what did I do? Holy smokes.
Sorry.
I must have a big thumb. So the changes that were made, so we actually wanted to reduce the amount of space that is required in the route reply, and we could do that by actually having essentially paired DODAGs. And so we wanted to have an easy association between the route reply and the route request. And the way well, we did that in a fairly straightforward way, which I'll mention in just a minute. The route request actually is sent from the requesting node or the originating node to finally received by the target. But when the target received it, what has happened is that the target now has a way to transmit packets from itself to the originating node. And the route reply then is transmitted back towards the originating node according to some path, possibly a symmetric path. And when it arrives, then the originating node has a way to transmit packets or transmit data to the target node. So there's a -3 document that's available, and actually this slide describes the changes between our previous -1 document and the 3. So the draft update it specifies this way of pairing the route request and route reply instances, and that allows us to eliminate a large field in the route reply message. And we have implementations in process. There's work, you can read it there, works on Kontiki with the Kuja simulator, which, by the way, I did not do this work, but one of the co-authors, SV Anand, has done this. So the implementation supports both symmetric and asymmetric modes. and they're making comparisons against Ripple storage mode. So we will make a more full report on this at the next IETF. This is work that's in process, and the intention is to actually make a demo at the next IETF. So the pairing works so that you can have the upstream is considered to be transmission from the destination or target node back to the originating node, and downstream the other direction. So the upstream instance ID for the route request instance is selected to be an odd number, and then the intermediate routers store that instance ID, and then when the route reply comes back, it's the route request instance +1, and so that makes it straightforward for the intermediate routers to know what is the originating node towards which they are establishing the reverse path. So that's the main technical difference that is now present in the updated draft. I'm not going to go into the gratuitous route reply. It's the same as it was before, but basically now we allow it to work with this way of doing a pairing between the route request and route reply instances. The implementation, as mentioned before, is done on the Contiki, and I guess it's supposed to be available on GitHub soon, and soon I guess means this year. So we are planning to run a lot of experiments on various network scenarios to see what the performance gains are and so on, and to put together a demonstration for the March IETF. I guess that's it. Any comments or questions?
Rahul Jadhav from Huawei. So one of the claim of the previous draft, I mean, I've not gone through the latest draft, apologies for that. The previous draft said that this enables asymmetric operations, asymmetric links. So basically,
Yeah.
But the way previous draft operated was by sending message from A to B and establishing route in the reverse direction.
Well, we want to, yes, we distinguish between asymmetric and unidirectional. So there's always a path to go back, but the asymmetry comes about by enabling the reverse link to have a much different metric or a much different, let's say, feasibility than. So you might want to have the best path going from source to destination by a much different mechanism than from destination to source. But we do expect at least that the control messages will be transmitted and the metrics evaluated in that way. So if you want to enable fully the more general case where there are unidirectional links, then I think additional work is needed.
Okay, okay. One more question. Regarding the simulation that was done in the Contiki, so which model was selected? Was it UGDM or DGRM? So I mean, basically, I want to understand if the default mode was selected. Which, I mean,
Okay.
if you use the default mode, definitely the previous draft at least would work. But yeah.
Well, for that, I have to tell you, I don't have that information since I'm not doing the simulation and
Okay.
work in Contiki. But it's Rashid, do you know anything about the Contiki platform? You probably should use a mic. I'm putting him on the spot here.
Oh, not at this moment. All right. Okay.
Okay.
More questions? No? Okay, thank you, Charlie.
Okay, thank you very much.
Right. Who read the document? Raise their hands, please. Okay.
5. Who wants to review this document or collaborate on it?
One.
Say just review.
Review. Okay,
Review.
just review. Yeah. 1.
One. Okay. 2. Thank you.
Actually, Pascal encouraged me to do this in the first place, so he should
Yeah.
review.
Yeah, but he was very willing to review.
I know the feeling. Thank you very much.
Thank you very much. Pascal, please. Pascal. Next speaker. DAO projection. Pascal? You can.
No, it's okay. So I'm Pascal, and with Cisco, presenting on the DAO projection. So basically, we've got this. Yeah, we've got this. Well, the REPL protocol, which actually enables a number of different ways of doing things. We just saw that we could actually turn REPL, and we knew it from the experimental RFC before, into a reactive protocol. We can also easily turn REPL into a centralized routing approach. And we've not done that before, but there are a number of applications for which this could be useful. An example application is industrial control loops. So what you build this REPL-based cluster of sensors and actuators and programmable logic controllers. And with this, you can enable control loops inside your factory network. But then at some point, you want to establish special path between this particular sensor and this particular actuator with guaranteed capabilities. For instance, you have a 6-dish, a TACH MAC layer. And with this MAC layer, you can program time slots so as to guarantee deterministically a path between this sensor, this PLC, programmable logic controller, and then back to an actuator. If you want to do that, you need a way to go and program the path, the routes, into the devices. So at some point, you need to program the time slot themselves, and that's not the objective at all for this work. But on the other hand, you also need to program the routes into the devices. And if you're, well, depends on which model you pick, but if you want to use routing, you need to go and program the routes. And so this is one way of actually using REPL as the protocol to install efficiently a route between a point A and a point B inside this low power lossy network. So what we do add to 6550 is really this capability to add routes on demand under the control of the route. But the route itself, and we don't have to specify how that happens, can be in touch with a PCE, centralized routing controller, which can tell the route which routes to install. So the first application for this is kind of obviously, because that's where it started, a way to compress source route path. If you've got a deep network and you're using non-storing mode, at some point you'd say, oh, if I've got this particular long line here on the right, and I know the capabilities, the memory space that you've got in those devices, I could actually save all this source route information in all those packets by installing, pinpointing some routes in those particular nodes. And since it's done centrally, it can be done with some awareness of how much memory there is in those devices. So you know you're not overloading those devices by this additional route. So the first usage, and there's some new text in version 3, is about compressing the strict source route header and making it loose.
Rahul Jadhav from Huawei. So the routing metrics also will play a role when you populate a path downstream. So how would you take care of that?
Okay, so the path is actually in non-storing mode is actually already decided by the DAO process, which creates the non-storing route. So the cost is done, its work is done, the topology is built. What you're doing for the non-storing mode is you are just compressing the expression of that path, but you are not changing the way you compute it. So the cost is passed, it's done.
Okay. So as I understand it correctly, so you're saying that since the node has already sent a DAO, it has already taken into consideration the metrics and decided the path.
DIO, yeah, the DIO.
And then it has already decided which
yes, the route knows that it would build this long source route header to go down this path. And I have a picture of that. So what you really want to do now is shrink the expression of that path in the non-storing mode packet by installing pinpoint state in specific individual nodes.
Okay, all right.
Right, but it's not a routing protocol. It's just a way of enabling a little bit of storing mode in a non-storing network so that you can transform strict source routing into loose source routing. Right.
Okay.
And this is doable because the root is expected to know the capability of the node. So it knows, oh, on this node I can install 5 routes. Let me optimize which node get which information. Now, the version 2 of this draft introduced a storing mode variation of that, which cannot be fully achieved until we send more information into the root about the topology. Because the non-storing mode only works on the information that the root already has, which is enough information. You just follow the same path. If you want to use the second technology, which is enabled by this draft, which works in storing mode as well, it works in both modes, you need some additional protocol element, which this draft is not providing, and we'll have to decide if we want to take this path and provide those elements within this draft or within another draft. And with these additional topological elements, you can build transversal path. And I have illustration, so let's go through those slides. Okay, so there are those 2 modes. We'll have to decide if we pursue this draft, whether we do only the non-storing, in which case we don't need new protocol elements, or if we also want to do the transversal path, which is really the interesting piece in some scenarios like industrial. And in that case, we'll need to talk about topological elements, how we express that to the root or to the PC. Like T's, this type of information, .NET. So what's new? Nothing much. I mostly did editorial work, fixed the abstract, which was still from version 1, so it only talked about source route. And so clarified what you can do with those transversal routes, which were introduced in version 2. So where I am is, we could work on the draft a lot, but at some point we really need to see what the working group wants to do about those 2 technologies, if you want to pursue them, and then we can work together on something.
So Rahul Jadhav from Huawei. One of the discussions we had on mailing list was, not related directly on this draft. The discussion was whether a mixed mode kind of operation be supported. Would this draft enable, by any chance?
Oh, it is a mixed mode, but it is a very, very controlled mixed mode, because the problem with mixed mode is same problem as storing mode, is controlling the amount of routes that you push into the devices. And that's really why we have those 2 modes in REPL. I mean, this discussion was like years ago, but the discussion was like this. Storing mode looks like a very good idea until you reach the limits of a node. And so we said, okay, so we could have, and I see the new work which is doing that again, we could have some intelligence so as to refuse a DAO from a child if the table is already saturated. And you could do that, but then you're pushing the prime on the neighbor, and maybe the neighbor has the same prime, and it needs to be pushed, and at some point there is no way, right? So that kind of pushes the prime a little bit and enables a bit more, well, a number of new situations, but it doesn't solve the prime. It just pushes the prime farther away. The approach it's very hard to make the distributed approach work. And so we can try, but it's very hard. The centralized approach is doable because the root knows which routes it's injecting into the network. Right, so it does that because it has information about the capabilities of the node. That's part of the expectation. You know which nodes you're talking about. You know how much state you can install on those nodes. You know the lifetime of this state. So it's very controlled. So that's the solution of the real problem, which is how do you know you're not overloading the whole thing? So that's the low-hanging fruit in this direction, I would say. But the real problem is much, much harder.
Thank you. More questions?
So I have provided slides which I won't play, but it's if you want to go through how these things work. I mean, there are illustrations in the coming slides which will be published, I guess, on the site.
Yeah, we can.
So I just.
Thank you.
Who has read this draft? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Who wants to contribute or at least review this draft? Who wants to review this draft?
1, 2, 3, 4, 5, 6.
6. And who thinks that this should be part of our work? 1, 2, 3, 4, 5, 6.
Okay.
Okay. So
Thank
we
you.
try to confirm this via the mailing list. Yeah.
Yeah.
Okay.
Thank you very much, Pascal. Here are the other slides from him. Okay. Peter?
Oh, that's great.
Yeah. 20 minutes. Oh.
Good morning. Lots of jet lag. Well, I tried to see if there's any interest in the work we did. It is about MIPL, and especially about the number of forwarders you have in a MIPL in a network. If you have lots of network which is very dense and there are lots of forwarders in it, MIPL forwarders, then when you want to multicast a message, you get an enormous storm of broadcast messages, and that's not really helping the performance of the network. So for those networks, it is important that you can reduce the number of MIPLs so that we call it the density of MIPL forwarders in the network is not too high, and you can have a reasonable number of messages. So that's what we try to do. Here I have an example, what you might like. So you have this network. If they're all forwarders and one will start the forwarding, you will get all the other blue ones will forward it, and then maybe only one hop is needed to go to the ones on the left, and from the ones to the left, one to the others. If you only select, for example, 2 forwarders in the middle, then the number of MIPL forwarder messages is reduced, and the performance of the network is much better. Yeah. How many forwarders should you select? Well, if you have a network where you have only one hop network, and then you think 1 forwarder is sufficient, and you would need 1 forwarder, because suppose that you have a broadcast coming from the right-hand green node, it will send it to everybody. They receive the message, but once the link is between the red link is down, then you're very happy that there is still a path which goes via the forwarder to the other nodes, which has this missing link. So having at least one, when you have MIPL and you want more reliability, having at least 1 forwarder also in a single hop network is encouraged. The other case is that you have a 2-hop network, and then you want at least 2 forwarders, I think, because if the link to one of the forwarders and the destinations breaks down, then you have the second forwarder to continue, so the reliability is really increased. We did some measurements in offices, and we saw that actually, even with stable links, where the RSI is very good, etc., that if you, say 20 minutes per week, you have links which actually crash, and then you have these 2 routers you just continue working during the year. Yeah. So what does the node maintain? We might try to keep it rather simple, and what we do is that we have count the number of neighbors which have the state that they are forwarders. State is FF, means I'm a forwarder. So every node maintains the number of neighbors that he has a forwarder with. And the other one is that he looks at the number of neighbors where the number of forwarders is smaller than the wanted number of forwarders, and duplicate, which usually in this stuff work is encouraged to be 2. And we have also n or above, where's the number of neighbors which is larger than n duplicate, because while you're constructing the number, selecting the number of forwarders, you will see that, well, it's not fantastic every time, so that when you have too many neighbors which are forwarders are selected within a certain area, you can reduce it. And also when the network configuration changes, so you can select other ones and remove ones, so to keep this reasonable. Now I have a very complex picture. Oh yeah, that's the next one. So what do the nodes do? They send a link local multicast, and they send their address, their SSI, the number of forwarder neighbors they have, the ender under and the ender above. They have and their own state, of course. CBOR format is used. Yeah, who doesn't? Only messages from, yeah, even graphs. So. So only messages from valid neighbors are taken into account, and on the message reception, you update the node and you execute the selection algorithm. Yeah, it's very complex. Oh, here's the here's the complex picture. I wanted to show that this NR under actually gives you information about the two hop neighbors. Yeah, so I have here two ones who are selected to be a forwarder. You will see that the one there in the middle, he sees that this number of forwarders is 2. You see on the others that they have the number of forwarders is 2. And then you have all these ones which are the neighbors which have their NR under, they can tell. And by selecting the one which has the highest NR under for all your neighbors, you may consider that this is the highest number of nodes you are helping with this forwarder. So what we do is we look at the number, try to select that node of all the neighbors which has the higher numbers of NR under. And that number may be the same for several nodes. And to break ties, we use the network address. So choose the highest one, for example, to have only one node of all the neighbors which are actually going to be forwarder. Yeah? You don't want all of them decide simultaneously. So this is what they done. Selection algorithm. So every node orders the neighbors, including itself, on the NR under number value and the address, so that you have this. And what do? You select at the first one, and if that's you, I become a forwarder. As simple as that. You also look at NR above, this first star ignore, and if this is equal to the number of valid neighbors, you know that all neighbors see too many ones, and you know that if you are a forwarder, you're just one too many in this company, and you remove yourself. Yeah, so that's how it works. There's also you want this to happen in a stable network, so you don't want to make decisions about networks which are constantly changing aspects. So what the criterion for that is to looking at all the neighbor messages, and if the NR under value is changing. If the NR under value changes, you don't do anything. Once that you see that during a cycle, all the messages are the same, with the same NR under for all of them, you say, look here, I'm stable, I can make my decision. Yep. Some examples. So if here I did some simulations of it, the distance between the nodes are about 10 meters. It is a 2-hop network. So the ones down below don't see the ones up above, but the ones in the middle apparently see all of them. You want to have a pass between all the forwarders. So what I do, I first make sure that there is one forwarder, and a forwarder can only be selected when he sees another forwarder. So which assures that there is a pass between all forwarders. Otherwise, you make it have a separate set of forwarders, which you don't want that. So here it looks rather nice. I don't think you can do much better than that. However, if the distance between the nodes is larger, so the density has decreased, then the things become a bit more less optimistic. You see that where the very good ones are, each node is marked with the number of forwarders it sees, and they all have at least 2. Where you see when the number of forwarders is 5 or 6, you may wonder if it should not be removed. Well, given the algorithm where we had, you see that actually some of them remove themselves. Yeah. So one of those there, the light blue one, has been a forwarder, but you saw that the density was too high. If the others do not go down, it means that on the edge, at least there is one node which only sees 2 forwarders, and he cannot remove himself. Yeah. So probably when you look at the evolution of the NRUnder, etc., you can do much more with all the data you get in the algorithm and do some refinements. I didn't do them. I have here another example also. So it is a very dense network. It's not too bad, actually. This also is not too bad. Yeah, they all see the two forwarded. So, well, I'm pleasantly surprised. And the questions and answers. Sorry. So, I wanted to continue the work if there's enough interest in it. If not, well, let me just stop it.
I'm Charlie Perkins, and I think this is a great idea. I was involved a lot with forwarding specification in MAN-A, and there's been a huge amount of work on this area. I mean, one of the terms that's used is connected dominating set, and you're trying to construct one. So I guess I have a couple of questions. I mean, first of all, do you really think that it's typically important to have more than one forwarder?
Yes, I mean, if you want at least 100% availability over a year in this room, and not when you switch it off, you say, oh, wait a quarter of an hour and try again. Yes, you need at least in one hop networks, at least one. And in larger networks, when you have multiple hops, you need as many forwarders, I think, yeah.
You mean you're saying you need duplicate broadcasters?
You need duplicates, yeah,
okay.
yeah. So, and duplicate one for multi-hop networks, I try to discourage that idea.
Okay, and I guess it's you know, your pictures are all sort of regular arrays of things. Overall, I think that could end up being a little bit misleading.
I quite agree. Even there are other misleading things. I mean, you may choose your network addresses such that the algorithm is improved. I mean, there are lots of things you can do. But yeah, what I also wanted to do is look if this, how far it's from the optimal. So how many forwarders you look for the optimal case. I didn't do all these things. I mean, I just was happy with this for the moment.
And so it's, I guess is it agreed that it's really, for this working group, mainly of interest for stably located devices?
That's a very good question. What is stable? I mean, the stable is with respect to the number of times you send your message out. So if you send out your MIPL, let's just like every 5 minutes, and you have about 20 neighbors, then stable is longer than 20 times 5 minutes. Yeah.
Okay, thank you.
Welcome.
Michael Richardson. So I'm trying to understand the diagrams. In this diagram, for instance, do the nodes on the far left can hear the nodes on the far right?
No.
No.
This is a multi-hop network.
How far do they hear?
Okay, can I point it out?
Sure.
So that one 0. Well, you see, they all see 2. So that one there, we see still, we see the one on the right.
So the one on the left marked 0 can see as far as the one marked 11. Okay.
He sees 2 others. So that one's 3, he sees the one to the left and the right.
Okay, that's great to understand. And I think you said, I was going to ask something about your definition of stable as well. And it sounds like you can basically, if the instability of the network, or if it's not fixed, or if it's moving, if it's slow enough compared to your transmission time, then it's effectively stable.
Yeah. So you can this can be set. So actually, I wanted to make the protocol such that dependent on what you see, you decrease or increase that.
Cool.
Yeah. Well,
so I haven't read your document at all, so I really have no idea. So does your protocol live on top of MIPL?
On trickle.
On trickle. So it's independent of the MIPL forwarding itself.
Yep.
Okay. So what I was curious about is that I know little about this, but they're the people that are trying to do beer to do multicast. I think that they would benefit from having this minimum set of devices that they could address that would then do that. So I think that would be a,
You're absolutely right. We
Okay.
discussed this with Karsten,
Okay.
and at first thought 2 months ago, they thought that it might help to reduce the number of paths that they had to look at. Yeah.
okay, cool.
It can be used for other ones as well. I mean, okay, leave it.
Pascal Hubert, I love this. So if you are looking for voices to say yes to continue, please continue this work.
Oh, thank you.
It looks to me that it's an interesting variation around a very similar acronym, which is MPR, the multi-point relays in OLSR. And I was just wondering, it seems to me that you're looking for an optimum for a certain radio condition. You know, the radio conditions change a lot, but there is also, if you're talking about non-power devices, battery-operated devices, then you may be draining the battery of the same devices all the time. And I was wondering if you could inject some variability in the algorithm, so you would periodically maybe not get the optimized thing, but optimized with the radio matrix is never perfect anyway, but have some rotation mechanism so that it would not always be 3, 11, 24. And sometimes it would be this guy above 3 and this guy under 11 on the left. Maybe more nodes, but
Excellent
rotate
idea.
things.
Excellent idea. Actually, it fits with one of my other thoughts, because when I see the stable solutions, if you move around the forwarder a little bit to another location, the whole pattern may look differently and you may remove of them. So I was thinking of actually an implementation where you may improve by moving them around. And so moving them around would be a good idea, I think, actually, in general. Yeah.
Okay, thank you very much, Peter. Who have read it up? He read it? Okay, 2. Okay, please read it and comment on the mailing list. Everyone sign this? Okay. Some more questions or doubts or comments?
No comments on the progress, no comments on the charter. Everybody happy to go forward as we are intended to? Yep. Right. Okay.
Okay, thank you very much.
Thank you very much. Have a nice day.
Have a nice day. We missed the other one. Where is the other one? Blue sheet?